overcomes darkness, knowledge distances ignorance. Following our tradition, I request all the dignitaries to inaugurate the event by lighting the lamp.
It should be in a clockwise order.
Thank you all. I request Professor Annappa sir to give a brief about the workshop.
Good evening, respected dignitaries on the dais, faculty members, student friends. Warm welcome to all of you for this 5 days workshop on frontiers in computing and its applications. This idea came to us when one of our alumni, the former IEEE NITK Student Branch Chair, 𝗙𝗿𝗪𝗀𝗃𝗁𝗃, told us, sir, there is a funding from IEEE Region 10 for conducting some workshops in the frontier areas, whether NITK would be interested. This will be funded through young professionals of IEEE Region 10. Then we discussed with Bhavana, then she is one of the faculty counselors in NITK, and Computer Society faculty counselor, 𝗙𝗿𝗪𝗀𝗃. Then we decided, yes, we'll apply for this, and it got approved. So they sanctioned $800 for this workshop. Condition is they will be at the end giving $400 if you spend $800. So we agreed. Then we started working on that, contacting it. The condition is we should finish by the end of June. That's why we have to hurry this workshop, even though students are not in the campus. Then we thought of doing it in a hybrid mode, enabling our students and others from outside NITK to attend this workshop. You know that sparse data is an issue that commonly comes during machine learning. Learning to deal with such data and make models that can learn with it is crucial for success for a career in data science. To become a successful data scientist, you need to understand the data perfectly. Today we have with us Dr. 𝗙𝗿𝗪𝗀𝗃𝗁𝗃, Senior Data Scientist at Ericsson. He will be sharing his vast knowledge and rich experience in working with sparse data in his talk titled Methods for Handling Low Training Data and Building Sparse Models after this inauguration. For quite some time, there have been rapid advancement in both 5G and blockchain. They claim to be the future technology and have achieved quite remarkable things independently. The fusion of these two technologies will be highly beneficial to the mankind. Tomorrow we will have an expert lecture by Dr. 𝗙𝗿𝗪𝗁 Das, Assistant Professor, Computer Science Department, IIT Jodhpur. He will be talking on 5G and blockchain technology for smart cities. In this aspect, I remember a year back, our director was presenting a proposal related to 5G for some technology innovation projects. It means how important 5G technology and blockchain in smart cities. With the rapid pace of development in all fields of computing, scientists are pushing the limits further and further. These cutting-edge technologies are being used worldwide for various applications, and knowledge about them is paramount for further success. On 22nd, Wednesday, Mr. 𝗙𝗿𝗪𝗁 Bhatt, Senior Director, Engineering at Google USA, will be addressing the participants of the workshop on the topic Frontiers in Computing. Light has always fascinated humanity and has inspired some of the greatest scientific moments. As we go smaller and smaller and study light and its behavior with other objects at the nanometer scale, a whole new world is revealed to us. On 23rd June 2022, our own colleague, Young and dynamic researcher, Dr. Mandeep Singh, Assistant Professor from Electronics and Communication Department, NITK 𝗙𝗿cie his𝗀𝗶𝗲𝗍𝗀, will enlighten us with a talk, Nanophotonic Devices, Challenges and Opportunities. It is unfortunate to think of human life without artificial intelligence now. Such progress has been made, but it hasn't been without its own challenges. As we push the frontiers of AI even further and expand the definition of what is possible even more, new challenges arise. Latest we are hearing about explainable AI. On 24th June 2022, Dr. 𝗙𝗏𝗪 Reddy, Associate Professor from CSE Department, NIT Goa, will deliver an invited session on research challenges in AI. So today we have speaker physically present here. All other speakers will be coming online addressing the participants. So I request you to enjoy the workshop with lot of learning, to enrich your knowledge and build better application for the humanity tomorrow. Thank you, Vananda.
Thank you, sir, for summing up about the current workshop. Today, we have an eminent personality with us, Professor 𝗙𝗿𝗪𝗁 sir, who was previously Director, MNIT Jaipur, a former Professor in charge of Hostel Affairs, NITK, a former Dean Student Welfare, NITK, a former Head of the Department, 𝗙𝗏𝗪 Department, and is currently serving as an in-charge Director of NITK, Suratgarh. I request our beloved Director, Professor 𝗙𝗪𝗪 sir, to address the gathering.
Yeah, good evening all the beautiful people joined physically and of course online. I think that some 40 who have joined online in a hybrid mode. To come out of this hybrid mode, it's over. I think we will not face any more problems of this pandemic. But still, people are afraid. Zindagi se move karte hai log, kono bana nahi chahte. So try to come out Next time we'll have a physical mode wherever, whether you go there or they will come in here. Respected dignitaries on the dais, Mr. Sunath, Dr. Ranappa, Dr. I can see your name. Bhavana, Professor Dr. 𝗙𝗿𝗶𝗃𝗁𝗍𝗍, all my friends here. Anappa's told student friends, call me all our friends here, not only students. He told the opportunity how he got it into this process of 5-day workshop. That is a smart way of dealing with the people. When you have the opportunity, grab the opportunity and take it, which will help all good people. We will be having only a credit of organizing such things, but the main beneficiaries are students. A computer engineer fuses electrical engineer and computer science into one program and technology, which makes the mankind very simple and technology sophisticated. That's why you have a department of electrical and computer engineering in the other universities. Only they did not get started. So why this? I was wondering why this computer engineer and electrical department of electrical engineering and computer science. So I found out the answer that computer engineer uses electrical engineer and computer science to make the reality into whatever the latest developments in the field of technology, which blends with the medical technology, which blends with the analytics, big data, blockchain, cloud computing, whatever you name, these are the two things which connect to the real life world. I think I see a lot of sponsors, IEEE. Somehow IEEE takes shelter under the Untitled Chapter of NITK 𝗙𝗿cie right from beginning, because student chapter of IEEE 𝗙𝗿cie is doing very well across in all the fields. So we have a galaxy of speakers for these 5 days. Take the advantage of that. I always tell all my students, we never had this opportunity when we were studying. There used to be some Sunday longer than Monday, professor comes, takes continuous classes, writes on the board. There are not PPT also. Somewhere it is overhead projector used to be there. There are very smart faculty also in that overhead projector also they will write and make you understand with the different color fonts what is the system is. But you are all lucky to have everything in your fingertips, palm top, laptop, or even on the display system. Understanding is very easy. You have to see practically. Reading, okay. I don't want to mention it as a coding and all. Reading and seeing the practical things is more important. That's what I tell my electrical friends also. Whatever you tell or calculate has to be seen physically that working, then only you will understand. You tell a lot of things, gigabytes, so many bytes, but is it possible to know physically what it is? Professor Anappa was telling about light. It's electromagnetic radiation system from 380 to 750 nanometers wavelength, where visible wavelength. Then your fiber optics goes into higher than that. What is wavelength? Simple thing is which or you pass a white ray to the prism, you will find colorful lights, out of which infrared and ultraviolet blue. That is at so many wavelength, and that wavelength you tap down and work it on to the signals. Light is being known to the humankind since thousands of years. The Makara Jyoti during the Kartik Masa in 𝗖𝗿𝗃𝗃 temple is even today also it is there. Thousands of years ago also it was there. Okay, people solve the mystery for their credits, but it is a light. So people understand what is happening there. You have a lighthouse here only. You have seen this lighthouse? What is it for actually? Guiding ships for what? It's not a huge ship. Why they should be guided? All the navigation system is there in the fingertips. They are not Vasco da Gama or somebody else who was the other guy. But why it is there? Guiding ships correct, but guiding against what? This is a very rocky coast. This portion from here to till 𝗙𝗊𝗪. We have one more in 𝗙𝗊𝗪 also. It is to tell the ship that don't come this side. So this was before your computer science or electrical engineering developed. It was developed and light was developed. You have a magnifying glass there, 3 magnifying glasses, huge magnifying glasses, so that the light ray reaches at some distance. Now the similar rays are doing with small fiber optic system only. So science and technology is developing beyond leaps and bounds. You cannot say that I am fully computer engineer or electrical engineer or ENC engineer or mechanical, whatever engineering system. You can just claim that, okay, I know I have just touched that, Like that fox tells, when it doesn't get that grapes, it says it's sour. That's what you have to do. Whenever you get it, whatever it is, yeah, this is my piece of bread. Try to take it out. If you don't get it also, don't worry. That is what the science and technology present. It's beyond. Because latest technology, they have found out that, aliens, flying objects and all. It used to be a story earlier, but now it's been reality. There is some mathematical calculations with the astronomical system. The genes of some of human species is equal to that aliens gene species exists. And that we are all aliens. And that species mix, they connect with the aliens or human genes get connected. I'm opening the Pandora box. We showed the Google and find out what is this connection. Because suddenly you have something different you are organizing. Humankind is organizing. Something different is being calculated. And they prove it scientifically that what they have done is correct. This tendency only aliens have. So we are aliens. Always trying to find something new. And you are part of it. And you have to study that also with other aliens. All these enigmatic people living with the high knowledge, I call them different types of aliens, quote unquote, and my personal view. Nothing comes in paper. So find out what is miracle, enigma, what is come from that? How it happens. I will read how it works book, Chota book. Book is Chota, but there are some 1,000 pages in there. Right from a childhood, the developed country child reads that how it works. How the pin works, small safety pin, you see. There is a hook and there is a spring, it has got that much flexibility only. Just you press it and it gets clipped into that. And how this, what is that pin? Pressing, staple, how it works, I see. You should experience that. I was wondering how that staple works. So when you press it, some two things comes out and it gets bent there. I was saying, okay, let me see how it happens. So एक बार ऐसा पकड़ के इसको press किया, the pin went into my this finger. Then I found out, okay, it goes down there. There is a platform that uses a small edges there. It bends and holds the paper. Simple thing. So we engineers should have that type of mind, how it happens and how I can change. I was very much fascinated by electrical system, the bulb, small bulb. So I was asking my grandfather, he is bit a mechanical and electrical engineer type, not engineer, he was in army and all. I said, Dadaji, how that bulb works? I said, current comes and it lights. We said, how it happens? And he said, you remove the bulb and see how. Put the hand in that, you know what current is. Oh, I don't know whether he has told it seriously or not, whether I was a 6th standard or something, and the old houses, Haveli type of houses, to enter the room, you have a small bulb. You have to bend it, not like 7 feet height one. Purana घर में देखा है क्या कैसे रहता है? That is automatically making you bend in front of the seniors. Bend करके जाना. There is a small light. When no one was there at home, I removed that bulb, switched on, put my hand into that. Then I understood what electrical engineering is. So people should be like that way. Creative. Understand what it is. Then your all the subjects become very easy. इधर रट मार के आते हैं ना, JEE, JEE, whatever pass करके, they get 100 and all. I think since yesterday I'm seeing the paper, everybody is 100. Huh? Nobody is 90. Everybody is 100. But the moment they come out here, that 100ness goes. Then they'll have to totally depend on somebody else's notes, somebody else's platform, somebody else's laptop, or खुद thinking capacity कम होता जाएगा. And that to first year the ratio comes down. The first 2 semesters and second semester marks you see, all this chemistry, physics, maths, the ratio is coming down. They are all cleared 100 in JEE, but still what happens? Because they feel that okay, मैं ज़्यादा जानता हूँ, सब कुछ जानता हूँ. It is not that. And if you are knowing सब कुछ, why you have to attend this workshop today? Because you are interested to know something new. And IEEE group, IEEE 10 region, I think Singapore, India, Asia comes in that region 10. They are all trying to help it out so that there will be a peaceful world, not this warfare world, controlled missile guided. I like the borderless countries when there is no, you don't have to spend for army and all. There is a peace everywhere, love everywhere. So the technology used for the humankind society for a goodwill. Take advantage of this 5 days program and enjoy your stay. Thank you.
Thank you, sir, for enlightening us with the importance of curiosity, creativity in the development of science and technology, and the need to attend the workshops. Now I request today's chief guest, Dr. Sumit Soman, Senior Data Scientist, Ericsson Global AI Accelerator, to address the gathering.
Everyone, good evening. Respected Director, Professor 𝗙𝗿𝗃𝗁, Head of Department of CSE, Professor 𝗙𝗿cie 𝗺𝗃𝗁𝗃𝗃𝗁, CS and IT departments, members from IEEE Arden, Professor Day-1, Summer, and the Affinity group, and their students. It's a pleasure to be here with all of you today at the annual ceremony of the workshop on frontiers in computing and its applications that has been organized by the CS and IT departments of NITK and is being supported by the IEEE Art and IP Group Bangalore section. I understand that as Professor Annappa and Director Sir has mentioned, there will be a lot of talks on the next 4 days, primarily around 5G, blockchain, nanophotonic devices, research challenges in AI, and leading industry trends. I urge all of you students who are attending the workshop, both in physical mode and in online mode, to make good use of these talks. It will be a great opportunity for all of you to engage and interact actively with the speakers and leverage their experience and expertise for your benefit. So I hope you'll all enjoy the talks and have a good time at the workshop. My best wishes for the success of this workshop. I hope this will have trigger a lot of insightful discussions into current trends in technology and will motivate all of you to pursue your aspirations as well. I also would like to acknowledge all the volunteers who have been involved in organizing this conference, including Professor Annappa and Dr. Bhavna. It is indeed a lot of effort that goes into organizing these workshops, and we definitely should acknowledge their efforts in doing this. So once again, I thank all the dignitaries for having me here. It is a pleasure to be part of this workshop and deliver a talk as well here. Thank you once again. Thank you.
Thank you, sir, for your gracious words. Now I request Dr. 𝗙𝗿𝗃𝗁𝗃𝗃𝗁, sir, Head of the Computer Science Department, NITK, to provide the presidential address.
So, Respected dignitaries on the dais, 𝗙𝗿𝚻𝗁𝗁, Senior Data Scientist from Ericsson, our beloved Director, Professor 𝗙𝗿𝚻𝗁𝗁𝗍𝗃, organizers of this event, Professor 𝗙𝗿𝚻𝗁𝗁𝗍𝗃 and Dr. Bhavna, and all participants, friends. So warm welcome and good evening to all of you. So this workshop for 5 days is frontiers in computing and its implications and its applications, its advantages. So if you see computing some days before or some years before, probably once we were doing our BTech, you might have studied, all of you might have studied 8086 microprocessor. So what is the width of the address bus? 20 lines, isn't it? What is the addressable RAM? 2 to the power 20 is 1 MB. 10 to the power 3, 10 to the power 3, 1 MB RAM. So the computers which come with 1 MB RAM, the first microcomputer which was built was around this 8086 microprocessor. It was supporting with 1 MB RAM, and that 1 MB RAM of probably some computer with some MBs. It used to cost us 80,000, 90,000 in 80s or early 90s. So now we are talking of 64 GB RAM, 8 GB RAM, 16 GB RAM. Just you see the development or progress in computing, and because of this development or this progress in hardware, we are able to do this deep learning and machine learning, artificial intelligence, all these things of it, this sort of things. And because of this, the technology also has developed a lot. So one joke I remembered here. So once grandfather and his grandson, they were discussing. Earlier, the zamana was very cheap. So I remember that we used to get a matchbox for 5 paise, and a chocolate for 5 paise, all those things. The grandfather was telling, you see, in our zamana, we used to take money in pockets and bring items in bags. So for a small money, lot of items we used to get. And that young boy, small child, said at that time CCTV camera was not there. So that way, technology once it's growing, so its capabilities, different avenues that it's opening, all those things are opening. As sir was telling, this generation is lucky enough to see all of those things. So whatever you want, you have those things, just at your fingertips. And all of you are equally smart also. Now, small children of 10 years, 12 years, they know everything on mobile phones, laptops, computers. They can do. There is. We used to hear in my dictionary there is no word impossible, but they have made it true. If I say I want to do this, I will not be able to do, but my daughter is able to do that. So that kind of verge of technology, all you people are. So that is the beauty of this time. So all of you have to make use of this and attend this workshop for 5 days. And the topic is also very nice. It's not like taking one topic and again covering some 3-4 things in that topic. It covers different topics. Blockchain is there, IoT is there, machine learning is there. So you will have different aspects to learn, and later you can connect them, you can encash whatever you want. So I wish best of luck to all of you for the next 4-5 days. Make best use of this workshop and bring really something good out of that, so that you can follow certain direction in your research field. With this, I thank all of you. Thank you all.
Thank you, sir, for highlighting the evolvement of technology and part of workshops in those evolvements. We have Dr. 𝗙𝗿𝚻𝗁𝗁𝗍𝗃, Assistant Professor, Department of IEEE, ISC Bangalore, from IEEE in Professional with us virtually. and I request him to speak a few words about the IEEE young professionals. Over to you, sir.
Yes, I hope I am audible.
Yes, sir, you are audible.
Yeah, thanks. Thanks very much. First of all, very warm welcome to all of you who are attending this particular 5-day workshop in person as well as in hybrid mode. I'd like to sincerely thank the NITK faculties, Professor Bhavna, Professor Annappa, and all others who have been involved in this event, along with also the student volunteers who have been the pillar for this organization. My special thanks to one of our current vice chairs, Mr. Samarth Bonthala, and he is also an ex-student of NITK, so he gave a lot of time and effort to organize this particular event. So special thanks to you, Samarth. And it's very nice to see a very good attendance both in online and offline mode. And I can also see Dr. Sumit, who is one of our YP Execom members. He's traveling in person and he also joining you as a keynote speaker. So I'll just currently I am an assistant professor in Indian Institute of Science, Bangalore, in the ECE department, and I am heading the lab which is known as IDARE. I am working on innovation and development of antennas, radars, and electromagnetics mostly. So data science is not really my cup of tea, but definitely we collaborate with a lot of data scientists in different aspects of our research. So in this particular, workshop, we are having IEEE YP Affinity Group, that is the Young Professionals Affinity Group of Bangalore section, as one of the co-organizers, I can say, for this event, because as I think Professor Annappa explained, the particular funding that has been obtained from IEEE Region 10 YP is one of the support for this particular event. So this I'll just briefly talk about this IEEE region 10 YP or student joint activity fund that is basically initiated to improve the young professionals and students collaboration within the section level, and this initiative also aims to provide platform for the students to network with section level IEEE young professional volunteers and get motivated. So this is just the IEEE art and side of the things. And this year, that this particular funding has been obtained by IEEE Hyderabad section, and I am talking about the region 10, so South Australia section, Karachi section, and Kerala section, and Bangalore section. So in the Bangalore section, we are having this collaboration with NITK, and this particular workshop is being organized. And I can see, I think Samartha has uploaded the slide deck. So just a little bit more information about our YP Affinity Group Bangalore. And it formed, as you can see, in the year 2000. And we had a very nice panel of chairs and vice chairs. And I joined this particular group in 2021 when I shifted to Bangalore for my job. And basically in the YP, we are having a very good mix between the industry and the academia members, from the graduate student members to senior members. So one question that generally comes up is who are basically the young professionals. So a briefly you can describe that after your BTech up to 15 years of that time frame, you can be IEEE young professional. And most of the cases, we have several active student volunteers and who join in the industry in different domains or different directions. So it's a really nice opportunity for them to stay as IEEE young professionals and get connected to this nice platform or nice network that has members from both industry as well as the academia. And this year we are having a lot of YP activities. Some more news will be coming up. You can follow us at our LinkedIn and our other social media pages like Instagram and Facebook. And we are having a young professional track at this IEEE Connect, which is the flagship conference of IEEE Bangalore section. And it's on the advanced technology, and it's basically an interdisciplinary track, you can say. And I'm very happy to share with all of you that it is having a very good number of papers this year. I think we are probably the second highest number of submissions in this particular year. And we are having a lot of webinar series as well as in-person events this year. Dr. Sumit, who will be speaking as a keynote speaker, he is also organizing a lot of events, and he will probably share something on that side also. So we are also having like this, this particular event, as you can see, YP in Student Industry Connect. And we also have our events in Global Summit and PHTC. So I'll request, I mean, I have Samarth with me in the virtual presentation mode. So maybe Samarth, you can chip in and share your experience in organizing this particular event, as well as more about your experience through this young professional section. So just I'm tempted to add at this point that Samarth will be continuing his higher studies in, joining in the higher studies in US very soon. Will be leaving the YP Affinity Group, but I'll extend my warm wishes to Samarth for his upcoming endeavors in this particular platform, because it is his alumni alma mater also. Okay, Samarth, please, you're welcome in the podium.
Thank you, Dr. Devdeep. I mean, it feels really good to be back and speaking at NITK, my college. I graduated in 2019 from ENC department, and currently I'm working for Qualcomm. So it feels really good being back in campus and helping the student branch organize this particular workshop. It was a great experience right from, I think we started planning this event in April. April 7th was the deadline to submit the proposal. Bhavna ma'am, Annappa sir, and myself, along with Dr. Devdeep, we sat together, brainstormed, and then came up with this entire proposal. And then we were successful, and we got to know that we were selected on April 20th. And now here we are organizing this workshop. So looking forward to having a great learning experience from this workshop. So personally, I'm also very interested in computing and would like to know and learn from industry and academia leaders in this domain. So yeah, I'm really enthusiastic about learning from this workshop and looking forward to the 5 days. Thank you all for joining, and thank you.
Thank you, 𝗙𝗿cie sir and Samarth Ghantala for giving an overview about the IEEE in professionals. Now I request the coordinator of the workshop, Dr. Bhavna Rudra ma'am, to deliver the vote of thanks.
Good evening, everyone. Before vote of thanks, let's have a memento session. So I would like to ask Annappa sir to hand over the memento to the dignitaries on the dais. Sumit, to Dr. Sumit, Senior Scientist, Direction. And now I request 𝗙𝗿cie sir to hand over a memento to Professor Director in Charge, Professor 𝗙𝗿𝗽𝗂𝗁𝗃𝗁 sir. Now I request Professor Annappa sir to hand over the memento to 𝗙𝗿𝗻𝗁𝗃𝗁 sir, HOD of CSE department. Now I request research scholar Saurabh sir, sorry, not the research scholar, sorry, Saurabh Bhatia sir to hand over a memento to Professor Annappa sir. Thank you all for gracing the occasion of this workshop inaugural session on the dais, off the dais, and who are present on the virtual mode. So I thank all of them for the are attending virtually as well as in person, some of them. And I thank Professor Director in charge, uh, 𝗙𝗿𝗃𝗁𝗃𝗃𝗃, our Heredity sir, for gracing this occasion and taking some time to come over here to attend this inaugural session from his busy schedule. I thank HOD of the CSE department, Professor 𝗙𝗿cie𝗺𝗃𝗁𝗃𝗃 sir, for giving his time for this inaugural session, as well as he has given the seminar hall for the 5 days to conduct this workshop peacefully. Thank you, sir. And anyways, sir, Dr. Sumit sir, you will have vote of thanks at the end because your session is going to be there after some time. Thank you all for gracing this occasion, and we will start the session mostly in 10 minutes. Okay, we will have a break of 10 minutes, then we will start the main session by Dr. Sumit sir. Okay, thank you.
I challenge you people, after the session of these 5 days, you can tell your grandparents or your parents or your educators what they mean by use of the signals. I am not getting the signals in the mobile. Today, the signals being had. Now the signals are cut. Tell them what that means. That is the service you are doing to the society. Mobile signal, they tell no. If the voice is not clear, signal keep nahi hai. Explain them technically as well as in what they understand by that. What you understand and how you will tell them. Then you are doing the profession.
Online part- Online participants can wait for another 10 minutes. The next session will start. Good evening all. IEEE young professionals invite you to a workshop on methods for load training data and building sparse models. As part of the 5-day event, Frontiers in Computing and its Application, it will be handled by Dr. Sumit Soman, a senior data scientist at Ericsson. Dr. Sumit Soman is currently a senior data scientist with Ericsson Global AI Accelerator. Prior to this, he worked with the Health Informatics Group at the Center for Development of Advanced Computing since 2011 in various capacities. He holds a PhD in machine learning from IIT Delhi and is a senior member of IEEE. He is an executive committee member of the IEEE Censors Council and the Young Professionals Affinity Group of the IEEE Bangalore section. He has published several research papers and has many patents and is an editor for the IEEE Journal of Research. He is also a voting member of the IEEE Standards Committee Working Group on Reporting Standards for in vivo neural inference research and the IEEE Industry Connections Group for Neurotechnology for brain computer interfaces. We welcome you to the workshop, sir, and over to you.
Actually, the slides are not visible online. I think you need to share it from the meeting as well.
No, but this is.
I think Shubham has opened the WebEx link from browser. So you can go to the browser and then click share from there.
Online you can sit and
I might need to, because I will change slides. You have this pointer.
yeah, this pointer is there, it works.
And
Is it I cannot everything. This is okay, this is okay. This place, sir?
yeah, put it on slideshow.
I lost someone, it is.
Yeah, it is visible. It's visible.
Okay.
Not this pointer is working.
Working.
What is working? The slide will have to change now. Wait.
Should I be sitting?
Yeah, you can see. Okay. So we can get started, and I hope people who are here can ask questions anytime. And those who are online, you know what is the best way? Maybe you write in chat and somebody will read it out, and we'll have a discussion on this topic. Okay. So we can get started. The topic for this talk is methods for handling load training data and building sparse machine learning. So we'll just begin with an introduction and maybe show my hand. Remember? Okay. Thank you. Okay. So we'll begin. So many of you are already familiar with what machine learning is and what you typically do in AI-based workflows and projects, right? So you have definitely, I mean, in some courses or where you might have thought about artificial intelligence, machine learning, and all these things. So basically, like we start with understanding a brief overview of what machine learning is, what are the ways in which it is typically done, and then we look at a couple of specific scenarios where you have either limited training data or you have need to build models that are fast. So I try to motivate what are these use cases where you need these kind of machine learning methods and how you can look at building them. And then we'll look at, at the end, we'll look at a couple of examples of where these kinds of settings are used. So this is basically just an introduction slide on what machine learning is, specifically what is supervised machine learning. Supervised machine learning is basically one specific paradigm or classification of machine learning, where we typically have data and we have associated labels with it. So for example, if you look at this on the top left here, you will see that you have a training data set, which is the data set in this box, and this will have two kinds of samples. Suppose if it is a binary classification problem, you can understand that this will have two classes which you need to classify. You have training data, which is, for example, in this case, two-dimensional data. And you train a model to predict this kind of data. So basically, you train a model to predict the label. And on a test data set, on which you do not know the label, you will use that kind of model to predict what will be the label. So basically, if you have a black and white as the two classes, for example, and the data is different, you will train a model and it will be able to predict for a new point whether it is class black or class white, right? So basically, what we are trying to do is build a model or an algorithm that will try to predict this on the test. That is the basic idea of supervised machine learning. So you have labels, you have training data, and then on the test data you get some prediction. So two specific ways in which we do supervised machine learning are typically classification and regression. Now, classification is an example shown here, for example. Now, these are like two classes. You can think of it, for example, that the horizontal axis is the height and the vertical axis is the weight. Let us say there are two features or two axes around which you wish to study the data. And you have various points. So various people in this room, they pick up their height and weight and we plot it here on this two-dimensional space. And let us say we want to divide you into two groups. One is being obese and non-obese. Let's just take that as an example. So all the people who are obese are in the blue dots, and all of them who are non-obese are in the black, in this purple colored plus symbols here. So now that you have these two classes, what a classification algorithm or a classification machine learning paradigm would do is that it will try to find this kind of a separating boundary between these two classes. Basically, you will train some algorithm on this data, and it will try to define a model, which is basically, so in this case, it will be the equation of this line, right? And this line, you will find it out in such a way that whenever you have a new point that you wish to predict, right, you will see which side of this line the point lies on. Right? So if it lies on one side, you can say it is obese, on the other side, you can say it is not obese. Right? So that way, a classification model can basically be built to predict two classes, or if there are more classes, this is a slightly more complex problem. And then the other thing you need to understand here is we have only taken two dimensions, right? This is just weight and height are two dimensions, as an example. But real data will be multidimensional. There will be a lot of other components that you collect data from. And therefore, it is not always as simple as finding this line, right? It is in higher dimensions, it could be a hyperplane, or it could be a non-linear boundary, right? So there are a lot of cases that could be, this is a very simplistic setting that we are trying to understand here. But if we look at regression, for it is a different case. Regression is a case where you want to predict the real value number, right? So for example, these are like the number of rooms and the square footage of a house. And these points represent the price of various things. We want to basically build a model to be able to predict the price of the house. So that is the regression setting. So now, like these are two common machine learning scenarios, data classification and regression. Most of our discussion will be focused on classification. And we will try to understand like what are the cases when you need to have data, what are the cases where you should, what are the kind of models that you need to build. So sometimes if this data is very large, like there is a lot of points, like millions of points, and also in very high dimensional space, like it's not necessarily to, let us say it's 10 or 12 dimensions, I mean 10 or 12 billion dimensions. So then it becomes much more complex to find any kind of this, right? So we will look at some of those cases and then how we should design machine learning models for those kinds of scenarios. That is what we are trying to understand. Now, other than what machine learning models you already have heard of, there is also deep learning models that you have heard of, right? These are more complex models, and the motivation behind using deep learning models is that the more amount of training data you have, it becomes more complex to train a model, right? You have to build a more complex model to understand what are the various aspects that are captured in the data. And if you look at computer vision, for example, you will find a lot of use cases, even in language processing. You will find a lot of use cases where you have these deep networks with large number of layers. And each layer will try to learn some intermediate of it. For example, if this is a deep network that tends to classify the image is of a car, of a person, or of an animal, right? That is what this network is trying to learn. So each layer of this network, this input, this image will be fed as input to the initial layer of the network, or to the input layer of the network. And all these neurons will sort of learn some activation of individual regions in the image. For example, it will be the first layer that will try to learn the edges of the image, right? Which are the important edges that identify a person, an animal, or a car. Then the next layer may try to identify what are the corners, right? So each layer in that manner will try to identify different regions of interest. This is typically our deep network would work. But what I want to show here from this figure is that you can see now the network complexity has become much more. It's a very large network, there are more number of neurons, and each of these will have connections between them. So it will be a large weight matrix that you need to store. So basically, if you look at any large deep neural network, you will have a very large number of model parameters. Right? Each of these connections is a weight, and that is the floating point number that you need to represent as the model in memory. Whenever you need to predict some new image, you need to take that model parameters and run it through the network and get the prediction, right? So all that storage and compute is basically challenging, and you might have already known that deep learning is usually done on GPU-based systems because they have large data, and you need to build train models, training the models in scalable time, right? So based on all of these challenges, what I want to motivate here is that with the number of data that is available or the complexity of the model as it increases, there are a lot of challenges in the way that we need to work with the machine learning problem. So we'll look at some of these challenges in this slides, in the following slides. So I hope it is okay till now. Anybody has any questions? Okay. So one of the ways in which we look at the complexity of a model is what is called as the Vapid Chauhan-Mentris dimension or VC dimension. So this is basically, now the next few slides will have a bit of math because we're trying to motivate about how these models' complexity is understood. And we will begin with simpler models, like we will look at what are hyperplane classifiers, the kind of that we looked at in the beginning. The first slide that I was showing where we are trying to differentiate two classes. We are trying to now formalize this notion of how complex a model can be, how many parameters it can have. So VC dimension is basically one initial, it's a very, it's been there for quite a while now, and there are different other kinds of complexity metrics also. But like it starts with Vapid Chauhan-Mentris dimension because it was primarily associated with a large volume of work around hyperplane classifiers and supported machine. So in very simple terms, VC dimension of a classifier, so F is some model that you have, like the kind that I was talking about, which will distinguish between two classes as an example. And that classifier has some model parameters which are given by theta. So if the weights of the model, you can take them as the model parameters. So let us assume that is theta. And you have a set of training points on which you sort of separate using this model, right? This model is trained to predict these two classes from the data. So now, if it is a very simple model, for example, if it's a constant classifier, like this is the base case you can assume, where there is no complexity in the number of dimensions, right? It's a very simple linear data that ends up only a constant, then it is obvious that it belongs to all of the classes. That might make it. Okay. So if it is a very constant kind of data, there is nothing to separate, right? So this dimension is 0. If it is a single parameter classifier, let us say you have data that comes in, the moment it goes up above a threshold, you set the class as 1, and if it is below that threshold, you set it as 0. It's a very simple classifier, and this one will have VC dimension 1. Alright, this is a very basic way of how you identify VC dimension. So the more number of classes that you need to distinguish, established and the dimensionality of that. Based on that, this BC dimension value will increase. So for complex models, if you have large number of model parameters, like the neural network that I was talking about before, or you have any other model which is trained on data with high dimensions. In those cases, the BC dimension estimation can be difficult because now see in this case, for example, single parameter you can easily estimate that the threshold at which it crosses will be 1 and therefore that BC dimension is a single value, it can be 1. But if it is high dimension data, it will be difficult for you to compute this dimension, it is not practical. However, in literature there are bounds on this kind of data. Although it is not exactly computable, but there exist bounds based on certain aspects of the data, and that we'll take a look at on the next slide. Okay, so this equation that you see here is basically the crux of whatever we discuss in the following slides. So any machine learning model, this is kind of a formal notation, and after this it will be more of like how to build the model and all the last kind of notation part of it. So given that you have some set of m training samples, and this set is called X, is your training data set, and it is in n dimensions, and the labels are denoted by y. Okay? So then, when you train a model with weights W, there is something called as the risk of a model. Risk basically means you can associate it with performance. Like if a model performs well, it has low risk. Let us take it as that is simplified. Risk is of two kinds. Risk can be empirical risk or structural risk. Structural risk comes out of how the model is designed. For example, if a model is a linear model, it is a simplistic model, but it may not be able to generalize it, right? So in that case, the structural risk of the model is determined by the nature of the model. If it's a non-linear model, it will have different structural risks. And empirical risk is the kind of risk that you associate with the test data that you get. So basically, performance metric that you evaluate. So if you evaluate the accuracy on a model on a test set, that basically determines the empirical risk. So the total risk, that is R of any model, is bounded by this equation, where empirical risk basically is determined by the test set, right? Whatever test sample you have or the model gets a prediction, that is the empirical risk. And another term, which is basically a slightly complex term, but let's just look at some of the values on which it depends, right? So m is the number of samples. So basically, if you see the denominator here, it is in this risk, the second term here, epsilon is directly proportional to epsilon, and epsilon is inversely proportional to n. So essentially, what it says is that if you have more data to train, and the other terms you assume that they are constant for the sake of discussion, you will generally find that the risk is inversely proportional to the number of training samples. This is an approximation we are making, but it is a valid approximation in the sense that if you have more amount of training data available, in general, the model performance will be scalable and this risk is low. The second thing that this depends on is called as BC dimension. So this term H is basically what is the BC dimension that we were looking around in the previous slide. But we will define it more formally, like we will have a proper bound on H also. And then the motivation here is that any model that you build, you have to take care of two things for the generalized performance of low risk. One is that you should have fewer number of training, you should have more number of training samples. And the second is that you should have the BC dimension reduced, or H should basically. So from this bound is basically presented in this paper by Pasnik and all, a lot of work on model complexity that you can look at. But we'll take this as a starting point, and what we take from this slide is that the total risk depends directly on the BC dimension and inversely on the number of samples. Okay? So I hope this bound is sort of clear why we are looking at this. All right, and one last thing that we define here. All right. So last thing is basically defining H. H is what is BC dimension. And if you have this kind of a plane, right? In the first slide, we were seeing that it is two-dimensional data, and on two-dimensional data, we plotted a line and the boundary, right? A line is basically a two-dimensional. So if it is a simple two-dimensional equation, you can represent it in slope-intercept form. So assume that this is U transpose X plus B. X is data, U is your slope, and B is the intercept. So any plane that general form, and this is for ease of understanding take 2D, but even if it's a general high dimension case, the linear hyperplane will have this maximum equation. Okay. So x, that is this VC dimension quantity, is typically defined as the ratio of the maximum distance a point can have to a plane to the minimum distance it can have. So we try to understand how we understand this. If you have a plane and you have points that are at different distances from the plane, okay, you take the maximum distance and you take the minimum distance and you find the ratio of this. That is typically how h is defined for these kinds of classifiers. But what we see here is that x depends on x, right? So the kind of points that you have, that will determine what is the value of x. So basically, what it states is that whatever training set, once your training set is finalized, only then we can compute x. If you change the training set, this will change, this bound will change, right? This ratio will change, and so therefore x will change. But therefore, to slightly simplify this further, what is already provided is that there is this bound on h. Okay? And this formula you might have seen across, that any hyperplane classifier, the h value is always less than or equal to this, right? So this is the upper bound on the classifier, on the VC dimension of a classifier, where r and d basically are terms of the radius, and the d is the distance of the maximum margin d, and r is the radius of the data. Okay. So, and n is the feature space of the data. So this r is what we can leverage in trying to bound the complexity of the model. So till now what I talked about was that building large models is challenging, and the complexity can go unbounded because it depends on the training data, right? You have different kinds of training data, the model performance will vary, and therefore it is difficult to estimate the VC dimension or any other such complexity measure of the data, right? So what you can actually do is that you can leverage this kind of a bound in the model formulation and try and get some additional benefits. How we do that, that is in the example. So any questions to this point? Is the overall idea clear and makes sense? Okay. So now we'll move on to how to build low complexity models using the idea that we discussed so far. That is how to use that bound of this dimension, and then we try to build models. Okay. So this is basically a very simple kind of classifier. This is basically two-dimensional data, and you can see that there is a plane that separates this. This plane is typically found by this kind of information, right? So how many of you here have looked at support vector machines or looked at this formulation? You would have some idea about this. So if this is the coefficient of the hyperplane, and these are slack variables. So basically what we are trying to say is that all the points on either side of this plane will be at least unit distance from the plane, right? This is what this constraint says, that the distance of this plane will be plus or minus 1 from these two boundary planes. And then this is the input space formulation, and we have some slack variables to allow for some flexibility in the computation of the plane. So you can change C and make it soft margin, you can make more soft margin. If you put a higher side of C, you are increasing the tolerance. This is the basic formulation of SQL. Now what we see here is that there is only a term So if we have this kind of formulation, we are only providing a bound on the distance from a lower group, right? We are only saying that the distance should always be greater than 1. But we are not enforcing any other kind of bound on the distance. That could mean that this distance can be higher. It can go to values, and there is no upper bound on this. That is the motive. One issue that we see here. And in the previous slide, I showed you that there is a bound on the VC dimension that can be sort of computed by this equation. Okay. So now, if we leverage this idea here, and what we try to do is that we try to enforce an additional bound on the distance. What will happen is that when you solve this kind of formulation, you will get additional benefits, that you will find fewer number of support vectors. basically, earlier you had a bound on the distance being greater than 1, and now you enforce an additional bound based on the previous distance. The mathematical derivation I am not focusing on here, that is mentioned in this paper that I have quoted on the next slide. But if you introduce an additional bound, such as this one, okay, we say that the distance is at least, h is greater than all these distances. And the objective function, we are trying to minimize h. So, this is basically a different variant of the SVM. Where what we are trying to do is, we are trying to introduce an additional bound on the distance of the point in the plane, and this is kind of an upper bound of the distance. And that upper bound we are trying to minimize the objective function. So by doing this, what will happen is that whenever the model will, whenever you train it using any optimization algorithm, etc. So this is a linear programming version, this is a quadratic programming version. And both of these are like published, so these are the references and there is some code also. But what we are basically trying to do here is that we have sort of introduced an additional constraint to the formulation. And how that will affect us is once the model is solved, since there is an upper bound, it will not tend to go and find too many points as support vectors. And that way, the model parameters will decrease, right? So if it's an SVM and you have like 100 support vectors to find, but you introduce these additional constraints and suppose it will not find all of them because of this additional constraint, right? So it will maybe find 10 support vectors, 20 support vectors. We have the results are included in this. And you will find that reduces the model complexity or will reduce the number of parameters. Right? So if it's an SVM, you do not need all these 100 support vectors associated Lagrange multipliers. You only need the ones that are found by the optimized algorithm. That is much fewer than the original formulation. So this is basically one motivation of how to use VC dimension to sort of bound the complexity of an SVM. This is one of the starting ways of doing the idea that we're going to talk about. Right? And once you have this is the input space formulation. You can go to the kernel space, you can look at various other ways of doing this. But this is basically the basic idea of how we want to introduce an additional bound and then say that the model will be sparse or less complex. So these two are of course different variants. So you have benefits of solving an LD, you have benefits of solving a QP. These are two, of course, from the mathematical point of view, you will get different benefits of using either of these versions. But basically, what we should importantly look at is that this additional bound that has been reduced by way of this constraint, or for example, by way of this constraint. So here, again, we are bounding this by the distance of the point, the radius of the point. And this tau is the upper bound, and that we are trying to minimize. Right? So basically, by doing this kind of manipulation with the training algorithm, like introducing these constraints, we are actually trying to get a model with lower model, this dimension, lower bound. That is basically the idea of what we want. And not only in this kernel space classifiers or SVM variants, this is also possible for larger data sets. Right? So one of the limitations, as many of you already know, that SVM is not scalable for large data because you need to compute the whole kernel metrics. But there are ways to get around that, you process it and you convert that constraint optimization problem into an unconstrained problem, and then you sort of iterate across batches of the data. And you use stochastic gradient descent solver of this kind of optimization problem. So if you have large data where you have a lot of features, right? And of course, if you have like very large number of samples given that case, the kernel need not be computed on the entire data. So you take the original optimized problem. So this idea is always there with SVM, with the original SVM also, you have a non-SVM, and you can sort of convert it into different libraries. So there are different libraries that already do this kind of a unconstrained problem with the SVM, and then you solve the optimization problem for large data. It is easier to do that. Right? So here again, if you have large data, you can always, of course, for the feature space, you can use different methods. Right? You can use random coded features, passport mapping, and from mapping. These are all common methods in literature. But for the scale of the data set, right, basically number of points, that will determine the order of the number of the size of the kernel matrix. So if you have 10k points, your kernel matrix is 10k cross 10. So that how will you handle? You do not need to compute it on the entire data. You use an unconstrained problem and you use stochastic gradient descent to solve this. Keep updating and get the model parameters until they converge to threshold less than some error threshold. Right? So this paper was something that appeared in Transactions on SMC in 2017, and the code is also available. So basically what we have been able to show is that this kind of approach that we initially proposed for kernel machines, we are also able to do for large data sets by doing this conversion to unconstrained program, and then you sort of do the STD as a standard approach for the large data set. So this was the stochastic descent of the SVM model, that is the minimal complexity machine that we were talking about earlier slide. So things are good till here. Any questions? Any comments? Okay, so I have not included mathematical details, that all derivation and convergence analysis is all that in there in the paper. So I have just basically put out the main idea that we have, and then how we understand. Now, of course, as I was talking in the beginning, that this is not just for kernel machines or like that kind of, even for network models, you can extend this. Now, how can you extend this idea? Basically, in any deep network or any shallow network, your final layer is a hyperplane classifier, right? The last layer is basically just doing a simple transformation on the final layer weights. So you can consider the final layer as a hyperplane classifier. And then you can use the same idea that we have developed till now on that final layer of the network. So for example, if this is a ELM is retrieval learning machine, so also called as random vector function things. So if it is that kind of network, it basically solves a L2 norm optimization problem. If you look at the literature, this is a fairly straightforward network. Initialize randomly and solve the L2 solution of the weights of the right? What we did here additionally in this paper is that we, in the final layers, and pre-final layer, we sort of introduced the MCM formulation that we were discussing, right? The bound of the complexity we were discussing before. We introduced that here, and then the rest of the network remains the same. So basically, here what we have been able to do is that for a large neural network, you take the final layer, and then you apply the same idea that we were doing before. Final layer is basically a hyperplane classifier. You can extend the same idea. Right? So this is how we sort of extend this to the final layer. But of course, the obvious question is that there are layers before this also, right? So we just don't want to do it in the final layer. If we want to reduce the complexity of the network, it is not necessarily only the final layer that we need. But layers before that are also all having parameters, right? So it doesn't make sense to just look at the last layer. But for layers before that, it is not as simple because it is not a hyperplane classifier, right? You have maybe 100 neurons here, you have 20 neurons. So it's 100 plus 20 weight matrix that you are transforming the space from the previous layer. So then it is not as simple as that. So therefore, we look at for the previous layers of any network or even deep network, we look at quantization. So for the final layer, you can do these kinds of things. Like you can do any complexity measure you take, you try and retain and do some optimization on that. That should work for hyperplane classifiers. But for the previous layers, I mean, in fact, even for large networks, like if you are CNN architectures or recurrent network architectures, there the complexity is also not directly computable. And there are works in literature that have estimated the complexity to be order of like number of layers and number of neurons. So that is kind of the order of the complexity of the network, but that is again then wrong. Right? So it is not very straightforward to work with this kind of idea on previous layers. So what we can additionally do is we can use the formulation that we have, but now instead of just looking at the simple multiplier that we have, we quantize the Lagrange multipliers and see. So basically, let us say quantization means you choose the number of fixed and variable, assign and unsigned number of bits that you want to use. Suppose you don't want to use 32-point floating representation, you want to use 16-bit floating representation. So now you quantize the trained weights, right, and use this kind of optimization problem. And now we will compare the performance, like without quantization, with quantization, what is the threshold that is being affected. And you have to choose a suitable representation like that. Like this number of bits that you choose, right, for the signed and unsigned part, that will determine what are the number of bits. If you choose like very few number of bits to represent, obviously you are doing a trade-off on the weights and the performance will get affected. But you have to make an optimal choice between the performance and this kind of quantization. basically by doing these things, you can start looking at how to decrease the complexity of larger networks. In this paper that has recently appeared on transaction on computers, we have sort of played around with this version and showed how the performance varies both in terms of training time and in terms of performance of the network with different levels of modulation. Right? So this way we have sort of looked at how we can leverage this idea for larger networks. But of course, a lot of work remains around trying to do it for different model systems. That is also a different area. Look at how to control model complexity and what all can be adopted. And then the end goal, of course, is that you have a model which has fewer number of parameters. So you can use it for different models. Right? Now the storage cost of the model is lower, and the inference time is also lower because you have fewer number of parameters. So the passing of the test data and number of computations that you do is lower. Right? So that are the kind of benefits that you get by using these kinds of methods with machine learning models. And eventually, this results in sparse-fitting models. Of course, you understand there are other methods for introducing sparse-fitting. But then this is something that comes from a machine learning model. Like, for example, dropout and all are methods that you randomly drop connections and see how the performance is. But here, like, it sort of comes from a more theoretical foundation around how complexity is understood, and then how you can leverage that for reducing complexity of networks. That is basically the idea of doing it. Okay. So this was the first part of the talk where we tried to look at how to reduce the complexity of models and how you can leverage DC dimension. Okay. Now the second part of this talk is basically what you do when you have low training data. So you may not have too much training data available. And in the first slide we saw that the performance of a model depends on the number of training data that you have. Right? If you have less training data, performance may be poor. And so therefore we want to look at generating more number of samples for training. This is typically what is called as augmentation. So data augmentation is one of the ways, and there are different methods you might have looked at in the future. But this is one method that we want to discuss here. This is on the slide after this. But you would have understood the motivation of doing data augmentation, right? If you can generate synthetic samples, and the challenge here is that you should be able to model the real distribution of the data, right? So if your data is a univariate Gaussian, then the samples that you augment should be from that same distribution. Otherwise, there is nothing. Actually decrease the performance instead of getting an improvement or right? So we need to do it in a way where it should reflect close to what the training data distribution actually is, and then accordingly you can always modify the method to be able to do that. Now, if you have looked at data augmentation methods, some of the basic basis points like smart data and all of these you might have heard about, but these are mostly restricted to like resolving class environments. Right? So for example, if you are doing prediction of breast cancer. So there will be very few images that have breast cancer, MRI images. But the number of images that do not have cancer will be much larger. Right? So a model that is trained to predict the cancer from the image may be biased towards the majority class. Right? And you would like that model to be specific and be able to perform on these kinds of scenarios when there is data imbalance. So SMORE, that is synthetic minority oversampling, and ADASIN, that is adaptive synthetic sampling. Both of them will try to reduce this imbalance and try and balance the data set so that the training does not get affected by the bias in data. But none of these methods are looking at preserving the distribution of the data, right? The key representative features of the data. And this is where we propose this method called as eigensampling. This is a slightly different way of doing data augmentation. So what I was trying to tell you before is that it is important that we preserve the distribution of the data when we are doing data augmentation. That is not currently looked at with the methods that we commonly have. They are trying to either resolve class imbalance, or those are kind of objectives that those kind of methods is looked at. So here what we try to do is a bit different. Suppose you have input data set that is shown here. Okay, this is the rows are the number of samples, column is number of features. Okay, let us say this is in some high dimension space, 100 features and 20 samples, let us say. Now you want to increase the size of this data set and you want to get new samples. This is the input, this is the output. Already you want more number of 10 samples. Now how will you get to doing this? One of the ways that we propose is that instead of working in this 20-dimensional space or this high feature space, you try to get to the eigenspace of the data. The idea is that if it is a classification problem, and there are like two classes. then it is possible, or in fact it is quite possible that any projection of the data onto a lower dimensional space that preserves the variance of the data in the respective classes will be more meaningful. Okay. So that is the motivation of looking at the eigenspace as one example, where we look at the projections of these samples over onto their eigenvectors. Let us say these are like two most significant eigenvectors. We take them and project them to this space. And now in this space, if it is a good space, if it actually represents the data variance across the classes, and you cluster the data, it will very neatly get separated into the two classes. So basically we are trying to leverage the information of the samples being in two classes. And we are now playing with the feature space to be able to get a separable space in low dimension. And of course in low dimension, the clustering problem is also relatively easy. Like you can visualize and look at other aspects of it. So you can define quantitative metrics here. And now once you have clustered, you have the cluster centers. Now you actually add new points like this. So for each cluster, you can add new points on the line that joins the point to its cluster. You can add it on the midpoint, you can add it closer to the sample, you can add it closer to the center. Anywhere you can add it. So that is again another parameter. You can add more number of points. Instead of just adding the midpoint, maybe you add 10 points on this thing. But it will always be representative of this class of points, right? It will be because this is well clustered. This is just an example to show the idea. It's not always that all these clusters will be very neat and very well organized in these samples. But the idea is that if you have these clusters well identified in this projected space, then you add new samples, it should make more sense to the data. And now the challenge after doing this is to go back to the input space, right? To did this in a low dimensional space. But the samples that you want should be actually in the input dimension space, right? We have to do this reverse projection. And if you typically look at how you reverse project from the PCA projected space, for example, you can use approximations that are available. More converse approximation is one such example. But the other way of doing is like, can we solve an optimization problem to go back here? And if we solve an optimization problem, we can add constraints, we can make it, we can introduce parameters. I'll show you some of the effect of doing all that in the next slides. So far the idea is clear. We have samples in input space. We move them to a low dimensional space where it is more separable. One such way of doing this is the eigenspace. The other way is like you could do some network and data mapping. You could use autoencoders, you could use any kind of, one hub of an encoder network and data mapping like this, where it is well separated. And then you do augmentation in this space and you add new points and go back to the input space by solving this problem that we will discuss. So now how does this work? So basically, I will continue with the eigen example in this example. So we took the samples, then we centered the data set, we did the eigenvalue decomposition, we did the compute the eigenvalues and eigenvectors. We choose it about a certain threshold if you want to preserve the ratio. Let us say the number of selected eigenvalues to the number of eigenvalues, this ratio. And then this is your projection matrix. We project all the points to low dimension space and do the clustering and find the cluster sequence. Okay, this is the first part of what we were doing. So basically we have reached here. We have taken the data, projected it to the eigenspace, done the clustering, got these clusters. Now we have to add these new points and then go back to the input space. How do we do that? So after this, the next slide is how to. So till this slide, you added the new points, right? The 3-dimensional points with the cluster. You obtain the cluster centers. Now you will add the new points. You can add them at the midpoint, or you can add them closer to the center, or you can add them close to the sample. This is basically like adding a point between any two points. You can take any point on that line and you can add. That's the formula. So if you have a well-defined cluster, and the cluster center is well represented, you should probably add closer to the cluster center, right? Because that way the representation is captured better. But if it is a bad cluster, you can possibly just add closer to the samples and add fewer number of points. So we are seeing how we can control the way in which we add the new points in the dimensions. And having done that, we need to get the labels of these new, because eventually we have to classify it, right? So we want to get the labels and go back to the input space. So for going back to the input space, we define something like a regression problem that we solve with SVR or subordinate regression. So if you have the low dimensional projection as X, and you want to obtain the input projection which is Z, is Z in this problem. You try to minimize the ectonome of Z, and you say that the constraints are such that the reverse projection, so GZ, G is a projection matrix, that is what you get in. So this projection is between xi plus epsilon and xi minus epsilon, where these two are user parameters. So basically what you're saying is when the point goes back from the low to the high dimension, that projection error should be bounded by these two points. Okay. So every time you say that the input, for every point, this has to be done. I mean, you can always parallelize this part. But you introduce these bounds, and then you can also introduce this softness constraint. So this is similar to what we do in this way. We have put that parameter. So now by doing all this, you can actually control how the input projection appears. For example, if you set low value of C, there will be less tolerance that will be admitted by computing the reverse projection. And that less tolerance will give you sharper results. I will show you in the next slide how you get some results. But if you allow more flexibility, you can have more number of input samples that you generate by this augmentation. So you can control the scale of augmentation also. How many points you want to attach to input. So this is how some of this works, and this is an example of how this will work. Okay, so you all know MS data set, right? We have 10 digits. So these are some digits of 0, some digits of 1 input data. And you want to generate more digits. So one of the ways in which we do this is we project it to some particular percent of the eigenvalue, and then we do a reverse computation without doing we use more kinds of stuff. We just project it back or use the inverse of the projection matrix and get them back. You will see that there is noise because the number of samples that you use and the number of eigenvectors that you are using that will determine how good this is. If you use all of them, you will get a much better result. If you use fewer of them, you will get noise and you come back to the input space. On the third column, you will see what you get using the method that I just discussed. We are using the same number of eigenvalues, but we are getting back the input projection by solving this optimization problem. This one we are solving and getting it back. So if you change the value of C, you will now see that the kind of samples that you get have much less noise. And these are also closer to the original image that you get. Right? And in fact, as I was telling you, so these are like the original points we projected in that. But as I was mentioning that there is an additional step that we are adding the new points here, right? These new points. Now suppose we reverse project the new points and we look at how they look like. That is the last column. Okay. So basically, if we look at the points after the new ones that we have added and we find the reverse projection, those are also much closer to the original. You will see that it is much closer to 0 and 1 and anything. So we are increasing computation here, and that adds up. But the kind of reverse projection that you get by changing these parameters, there are many more benefits. Right? So this is a very simple example to understand why this kind of method would work better rather than just pulling input in space, adding new points and pulling the parameters. So this is one of the ways in which we can increase the augmentation rate and also control the quality of the data that we augment. Basically, by changing the parameters, you can change the quality of these projections that you get. So in images, it is easy to understand because you can look at them and it makes sense that this image looks closer to 0 or closer to 1. But for numeric data, that is not always very easy. So, but for numeric data, you can compare accuracy, for example. And this is a case where we have a lot of data sets from the UCI repository. And we chose different methods of augmentation. So eigensample, then these are Smoot and Addison and bootstrapping. Bootstrapping means simple resampling and retesting. Resampling with retesting. So just use the number of samples by random multiplication of the data set. So this is like the 5-fold accuracy and the mean and standard deviation of the accuracy that you get. And so on many of these data sets, you will find that there is improvement compared to doing it with other methods like Smoot and Addison. This is basically performance in terms of numeric data, where looking at that visual example is easy, but understanding how this will affect performance for numeric data, that is something that is shown on this. So that is, I think, more or less what we had here. This is, okay, so before I click, so this is the last slide which is stopped. And till now, like I covered what all was there in papers and like what all these methods could do. This is one example of what we try to do with this kind of data. So, many of you might have heard that there is biosimilars data, right? Where we have this kind of headset that is a younger picture of Maria. So we are wearing this kind of headset, and there is a wireless, there is an adapter that is connected to the laptop. So all these signals that are generated are captured and related to the laptop for processing. Now, these are the same challenges that we are seeing here. There is no training data, like because if you cannot replicate all movements, and then you need to build a model that should not be very heavy, right? Because this is like on devices. So I'll play this video and then I'll talk about what we are trying to do. Okay, so basically what I'm trying to do is that I'm trying to write some character on the screen, like by doing various moves. All the data that will be collected by this device, trying to draw something on the board. And there are a lot of other applications this could be used in gaming, in assistive technology, and all that. But this kind of data, you are trying to identify 4 classes. So here, like you're seeing sometimes I'm linking, sometimes I'm cleansing law, right? Sometimes there is IEEE. All of these, you can sort of build a classifier to identify these 4 entities. So rest and all of these movements, right? So these are 4 classes, and you have a data set which does not have too many samples, right? If all of these people in the room, I ask you to record 100 times all of this for training data, it will be like very cumbersome for everybody to do, right? So you won't easily find large number of samples with such kind of data. But therefore now you could look at the augmentation methods that I was talking about in the previous slide. And even for the model that is developed, right? This is on a laptop, but this kind of use case can also be done on mobile devices where compute is limited. You can't do it on a server, you have to do it on the device. So then you have to look at how to use sparse models that are low. So some parts of what I discussed were used in this pipeline also. And this I want to give you one example of how all of this can come together as an application and you can use it for the demo. This is one interesting application. Of course, there are a lot of others like text and images, and there are a lot of deep learning applications. So you can always use them in those applications when you get them. Alright, so finally we come to conclusion in 2 directions. So basically what I talked about, there are 2 things. One is that model complexity is important. So therefore, whenever we deal with large data or large models, the training and all needs to be done on GPUs or NVIDIA. But this is going to change now, right? With all the communication advances, you will probably hear about this in later talks also. A lot of the training is now moving towards HTTP. You have to do not only the inferencing, but the model training also needs to be used for edge devices, low compute platforms, hardware platforms, and all of these kind of things. So therefore, like, you cannot have very large models. If your computation model is like 300 MB file, you can't put it on a mobile, you cannot download every time and run it. You need to have models which do not have too many parameters. That is why all this sparse machine learning is important. Now you can do it in a numerical way, it's much more like foundational in how you will be able to also improve visualization. Whether you want to look at these kinds of methods. And in this talk, I primarily covered looking at it through the 𝗙𝗍𝒻 dimension board, building the scalable variant tools, 𝗙𝗍, and also you can use them in deep networks. In the final year, you can incorporate the same concept, but in previous year, you can do it one dimension. And of course, also the availability of training data is important, right? So difficult to get a lot of training data for. You cannot say that unless I have 1,000 samples, I can't do model training. That is practically true, but it is difficult to collect so much of training. Therefore, you have to look at synthetic methods of augmentation. If you are doing computer vision and you already know this, that you don't have data from so we have to look at efficient methods of data augmentation, and that is some of what comes across in eigensampling. And therefore, future directions are basically looking at all these. Now, training, earlier what you used to do, you should put all data to a server and you should train. And then whenever you have a test data set, you do the inference, send the inference back over the network, and let the actuation be done on the device. But now you have to look at distributed training, right? Now it is not as simple as pulling all the data on one big server and doing it. So if you, for example, now your mobile phone has a camera and you take an image, it will show you it's a chair. How does that happen? The model has to, A, has to work on the device. That is one. But now, for example, you take an image of a chair, I take an image of a chair, it should predict it with better confidence. Right? All this training data also has to be. So therefore, the training now has to be distributed. All this data cannot be pulled onto one server because there are challenges in compute, there are privacy restrictions, there are security restrictions, right? So all of this data is private user data. So therefore, now you look at federated learning, there are a lot of new ways in which this distributed privacy learning model is being used. And therefore, that is where some of these techniques will come into play. Second thing is addressing data change in time. So this I give you another example. See, before COVID, all of us did not used to do so many video calls, right? It was very rarely that we used. Now all the time there is so much network traffic that when you start a video call, half of the time you are asking each other, are you audible or are you in the call and all of it, right? That is because there is a lot of change in the distribution of data. Earlier it was much more structured. Now, like after one lockdown, everybody has started to use it at a very large scale. So the same model that predicts how one is said, like the telecom cell is, you have to do some actuation to keep certain quality of service. Now that model has now entirely different distribution of data. So therefore, again, you have to change how that model will adapt to this kind of risk. So detecting this kind of risk, resolving this, these are all important challenges. And how, that is why what I'm trying to motivate is here is the way these machine learning models are trained will be changed. That is why you should look at all these directions. Other than as I mentioned, that security and privacy concerns are also very important. So all the future methods for model training will take into account these considerations. And therefore, some of the important aspects that we covered, like data augmentation, looking at complexity of models, will play a key role in addressing these challenges. Of course, there are a lot of newer methods, but what I want to cover here was that you will have some idea of how to look at model complexity for different kinds of models on the VC dimension approach, and then also look at how we can augment data sets by using INSR. These are what we basically. So I think that is all for the talk. And any questions, then all please feel free to ask now, or you can email and ask as well. I think I will pause this point, and then any questions, please feel free. Yeah, good.
Quantization for reducing the model complexity. Can you use pruning with quantization? There is a technique called pruning to reduce.
Right. So the work that I showed on the slide, there we are primarily not looking at pruning, but it is definitely a way to do it. So what we did is that we basically just varied the number of bits that we use to represent the weights, floating part and the real part. And then for the optimization, we looked at the method that I will discuss now. Of course, for deep networks, quantization in itself, there are a lot of bits. There is very little pruning is nonsense. But the way the motivation behind doing pruning is similar to the notion of dropout, right? You think randomly drop some layers and then see how it goes. So that is one school of thought, and that is a valid way of looking. The other way is like, can you use the training algorithm to introduce some smart sequences? That is what we think. Right, so of course, depending on the kind of network, what you use will vary. But yeah, total these are ways of doing it. It is always good to have a combination.
Item sample method, when telling them we have to project back to the new space. Is it really necessary, or you are projecting back just to get the clarity of the images which is near to annotated?
Okay. So that depends on the use case. If it is just, if we only want to classify ourselves, if it's a model, then we will not necessarily get back to the input. Build it in that program system. But assume it is some kind of medical diagnosis, medical classification, like when we're talking about cancer detection or MRI. So then what will happen is you will need to come back and show the end user what is the data sample that you augmented. So then he will ask you the question, how does it look like? What is the reason? Why is your model doing well? So there you can actually use this method, get many more samples. So it depends. That's what I'm saying. It depends on it. Sometimes the end user might want to actually see what synthetic data looks like before we even build a model. Plus, I think somebody was talking about before also that extendability of these models is important. Right? How well the model, you will be able to understand why the model predicts on a particular sample in a particular area. So that is where these kinds of reverse augmentation and even of course there are a lot of methods for extendability in media. Like webcam is there is layer wise resonance propagation. All of these methods are looked at from the point of understanding how the network works. Correct? Where those kind of use cases will require you to go back to input space, see what the sample looks like, then take a column whether you want to use it for training.
So there are chances that if we reverse augment the performance may increase.
Yes, usually that's what in the results we saw. We got it back to input space and then we did the classified training on the augmented data. And that's how we got the net performance on the augmented data.
Any questions?
Anybody has any questions? Questions are welcome.
They can put it in the chat also.
You can put it into the chat as well.
I think somebody is there. Chat, yeah, right.
No question there, but feel free to ask even now or if you want to email and ask. Any questions from the people here? All clear?
Yeah, basically, like data augmentation technique. Like you showed for the 2-dimensional IRS data. Can this be applied for medical which has like 3-dimensional? Like,
Volumetric data. Yeah. So see, at the end of the day, if you have 2-dimension n cross n, the feature space is n cross n. If it is n cross a, the number of dimensions is increasing. But looking at projections continues to be the same setting. So all of these are not important dimensions. Some of these will have representation. So for the data implementation, it really doesn't matter whether it is 2D, 3D, ND, but we are looking at the total number of dimensions and we compute the eigenvalues. Yes. Okay, so if there are no further questions, thank you all for your time.
Thank you all for attending the session, and thank you, sir, for the tomorrow evening by 5:30 we will have next session. The next session is on 5G and blockchain technology for smart cities by Dr. 𝗙𝗿𝐺𝗻𝗃 Das. And tomorrow's session is on 5G and blockchain technology for smart cities, and it is handled by Dr. 𝗙𝗿𝐺𝗻𝗃 Das. Please join at 5:30. It will be from 5:30 to 8 p.m. Thank you all.
Thanks for joining.
I think feedback link will share it at the end of the 5 days. And once you fill the feedback form, we'll send your certificates. Hope that is fine.
Yes, Samad, that looks good. Thank you, Samad, and thank you everyone for joining. Tomorrow, everybody be present 5 minutes prior to the session, around 5:25. See you all. Take care. Thank you.
Yeah, thank you everyone.
Persons who are attending. Samad?
Yes, sir, I am there.
Okay. What about the attendance?